Okay, audio still good? Everyone can still hear? Perfect. All right. So this week we're going to look at this week we're going to talk about natural language processing and look at as kind of an overview what it is. We're going to look at historically how computing has evolved around this particular aspect of AI. So the Wikipedia definition of natural language processing focuses in on the subfield of linguistics and taking language and personal interaction with a computer and a human, dialoguing either through voice or through chat. All right, so if we go way back to the 1950s, when Alan Turing had the original hypothesis around trying to get computers to mimic human conversation and human interaction, we sort of had a very basic natural language processing called symbolic. And basically what you were doing is hard coding your rules into the AI system. So these rules essentially were a bunch of if statements where if you said this, then this would be the response. If you said that, that would be the response. And that is extremely problematic when you're talking about how we as humans interact and communicate with each other, because that's really not how we talk. We're not a bunch of robots that just kind of always say the same thing, that always say the same thing the same way. And we're going to talk a little about that as we go. And I mean, you can see in this example, that's just a horrible failure in the NLP system, where it doesn't really matter what a person says. You're just kind of responding back and saying, okay, thank you for your feedback, right? Again, you're not listening to your users. You're not really processing or understanding the context of the language, right? And then in the 1990s, we started getting into doing what's called statistical natural language processing. And this is where we started using things like Bayesian inference to try to set weighting on different keywords, but it still was very much rule-based. So it was smarter than before, where we're actually like hard coding exactly what to say, but it still wasn't perfect, right? Because you're still kind of dealing with human language where we're not speaking like we're talking to a computer. And I think this video kind of really sums it up. So you'll notice in this grocery store, everything's ordered by color. So we have all the purple products, all the white products, liquids under $10, kind of like the stuff you see on an online e-commerce site.
Hello, just after semi-skimmed milk.
Your search for semi-skimmed milk returned 0 results.
You don't sell milk?
Your search for milk returned 52,256 results. Your top hit, milk of magnesia.
No.
Milk floats of yesteryear.
No.
This milk-themed family wall planner.
No, sorry, I'm just looking for, normal milk.
Couldn't find what you were looking for.
That's what I'm saying. I couldn't find it, so I'm asking you if you could...
Advanced search.
Alright, let's do this. Keyword, now, go.
Yeah, okay. Milk.
Please narrow your search by using one of the following filters. Kayaks, packet 12, self-cleaning, breakfast and condiment.
That one. Breakfast.
One result.
Milk, skimmed semi.
Semi-skimmed milk. That's what I first asked you for.
It's milk skimmed semi.
So that's kind of the type of systems we're talking about that were basically 10 years ago, right? Where they had to be very specific, very clear. The fact that semi-skim milk versus skim milk semi is just a reverse in words is actually a real thing, right? So when we talk about what's changed since then, the majority of natural language processing systems today now use neural networks, which I know you're going to talk a lot about in your other courses. And essentially, what we're doing is we're now implementing machine learning to figure out the rules as they change. And that's sort of the, you've probably heard the old I before E except after C in the English language is how we write certain words, except there's over 900 different exceptions to that rule. So all of that sort of stuff kind of culminates, and it becomes very challenging to actually figure out what the correct rules are that should be applied. And so by using neural networks, we now have automatic learning that is building that statistical model around the inferences that are given and the utterances that are being said, which then over time trains the model continuously, and that allows it to do things like pick up different dialects, pick up different regional sayings. You're constantly training the model that maybe there's a place with a certain name, right? So maybe you want to know where the Old Dock is. Well, perhaps in one city, the Old Dock represents a physical location that's a wharf or a pier out on the ocean. And in another geolocation, the Old Dock is actually a restaurant. So this contextual awareness of the languages and the utterances and the key words that are being described to the system matter greatly. And this is why we really needed natural language processing in order to essentially understand how people converse. Right? Watson was a research project that IBM spent, I think, about 7 years doing. And they wanted to tackle the problem of trying to solve Jeopardy. And for those of you who have never seen the game show, Jeopardy is actually a very difficult game show for humans to even understand what is being asked, right? The whole point of the show is to link potentially dissimilar topics together. So trying to formulate an answer, which is in the form of a question on Jeopardy, is a difficult process for a person.
You are right.
We actually took the lead. We were ahead of them, but then we started getting some questions wrong.
Watson?
What is leg?
No, I'm sorry, I can't accept that.
What is 1920s?
No.
What is chic?
No, sorry. Brad?
What is class?
Class, you got it. Watson?
What is Sauron?
Sauron is right, and that puts you into a tie for the lead with Brad.
Watson went on a tear.
Watson?
Who is Franz Liszt?
You are right.
What is violin?
Good.
Who is the church lady?
Yes. Watson?
What is narcolepsy?
You are right, and with that, you move to $36,681.
I mean, doing things with fixed rules, like playing chess, was something that I think it was like 1984 when the reigning grandmaster of chess was beaten by a computer. But it wasn't really until almost, I think it was 2011 when this aired. So it's really only the last decade that computers have been able to compete at a trivia show where they actually have to figure out what is being asked. And so there's a couple of key concepts here. So basically, and I'll play a couple of snippets just for those who've never seen the show so you can get a sense of how it runs. But basically, Watson from IBM, this is where it was created, right? It was originally started off as a project to answer questions on Jeopardy. And some of the key things that they came up with was they used neural networks to figure out a confidence level of all the possible answers that you think someone is saying through this short utterance, right? So as the host gives the question, when you actually watch this video, they talk about how sometimes they're having to go through like 100 terabytes of data all within a second or two to piece everything together. And one of the problems they had was people were still doing it faster than these massive, massive computers that IBM put in, right? So you think about it, you think trivia, if you have the internet, you can figure out any question. And that's true, but trying to figure out the context or the meaning of the question it was really the challenge here, right? So just to pause there, because he didn't actually read the question. When you look at this, you're pulling facts from 3 or 4 different sources, right? It's not a simple, straightforward query like who wrote Dracula, right? You're having to be aware of the contextual reference to things like pulp culture and everything else. So we'll move on from here. And I'm going to talk a little bit more as to why this is so challenging, right? So essentially, as we discussed earlier, for about 40 years, we tried to create rules that we could program into machines to talk and speak and interact like humans. And we failed miserably. Even after we had all of the recent processing power and computing resources, and we connected the internet together, we still really couldn't come up with a way to come up with fixed rules for the English language. Okay, now I'm going to talk just about English in these examples, but it really applies to all languages, right? Every language has its own dialect. It has its own rules. You have different ways of saying things. In English, you have these things called contractions, where you can take can and not and put them together, and it's can't. And we're going to talk about sort of this multidimensionalness of the English language. But again, this does apply for pretty much any language out there. And so when we talk about natural language, this is what we as humans use to converse back and forth. And really there's 3 different dimensions here. We have syntax, semantics, and pragmatics. And these 3 dimensions all come together for us to communicate, right? And so if we forget about communicating for a second and just talk about what is syntax, right? So I have an icon here of a traffic light, and I'm not sure, depending on where you are in the world, they may not look like this. But in North America, this is a traffic light. So right away, we potentially have a disconnect with cultural understanding of what this means. Because depending on where you are in the world, you may not use these types of traffic control devices, right? Whereas for someone in North America and Europe, these are just sort of, everybody understands them, right? So if we were to look at it from a syntactical point of view, right, we're say that again, in North America, we have green on the bottom and red on the top, and potentially yellow in the middle, right? And then again, there are 2 or 3 different exceptions to this rule, and we'll talk about those in a second, but I want to keep this really simple. So syntax is defining location and placement of the language. Okay, and in this case, we're conveying language through a series of different lights. Okay, the semantics are that when the light is green, that means go, and when it's red, you stop. Right? This is what we're taught when we start driving. That's the basic rules of the road, if you will. But now we get into the pragmatics of a traffic light, right? And essentially, when the light turns yellow, you're supposed to slow down, and you're supposed to try to stop if you can. And just because green means go doesn't mean that you just kind of floor it when it turns green. You need to be aware of your surroundings. Take a look, because you may have someone that has the last condition applying where it turns red, but it turns red at a point where they can't necessarily make it through the intersection safely. So, I mean, there could be bad weather conditions. It could be slippery. It could be a snowstorm, depending on where you are. There's a whole bunch of, again, exceptions to the rule. So to say that green means go, red means stop is a general rule, but pragmatically, as you're actually conversing with this traffic light and you're seeing what it's doing, you have to take into account the contextual awareness of what's happening outside, right? And this is one of the reasons something as simple as this has been a big challenge for those that are dealing with autonomous vehicles, because it has to not just understand the semantics, but the pragmatics and how humans will interpret the pragmatics. And this is why that's been such a difficult piece to try to solve, right? It's not so much that the rules are complicated. If we were going to create a system that was only autonomous vehicles, in other words, no people could ever drive on these particular zones, it would be much, much simpler, right? It'd be almost sort of like an automated railway type system as opposed to an automated New York City congestion, traffic chaos, right? So, and again, some of the other rules is that in Canada, again, in actually most parts of Canada, because not in all provinces of Canada, you can make a right-hand turn when it's red. So you just have to make sure there's no oncoming traffic on the left-hand side. So again, what we tried to do with natural language processing through the first 50 years was address this, right? Try to come up with the syntactical rules. Try to come up with the semantics. But the pragmatics is really where we were tripping up, right? And I'm actually going to talk through a few different examples using human language that really illustrate why this can be so difficult, right? So when we talk about syntax in natural language processing, this roughly equates to grammar, although that's not quite correct. But I'm going to use the example of word order. All right, so in other words, how you use and how you sequence words in a sentence greatly impacts what you're trying to convey in that sentence, right? So, for example, when you say, that was easy, right? You're making a statement. You're saying, whatever I was doing was pretty easy for me, right? When you talk about an easy way to learn, you're talking about the term easy is applying to whatever that was you were doing, right? So if you find this video is an easy way to learn, if you find attending classes and asking questions from a teacher is an easy way to learn, that's now using the same word but changing how it's used, which then changes the construct of what's being asked, right? You can also ask a question. So in this case, easy is still at the end of the sentence, but now it's a question, right? So we're saying, is it easy? Is the test going to be easy? Is it going to be hard? What is it, right? And would that be easy, right? So again, is something easy? Would something be easy? Those are two different questions. Now, granted, there's other things that are in these sentences that can give clues to what's being asked, right? So, for example, if you're asking, is it easy? You're saying, is whatever I was talking about before easy, right? So, in other words, someone has already done it. It's been achieved. So now you're asking for input. Did you find this easy? Whereas, would it be easy? You're saying, what do you think? Maybe you know, maybe you don't. I'm looking for an opinion. So the response to that would be significantly different, right? And now we could also do something that syntactically is completely wrong in the English language, but is sort of how Yoda would say, oh, sorry, that was, right? So easy does it is a different comment. Sorry, I lost my train of thought there. Where you're telling someone to take it easy, to slow down, to pace yourself. And easy does it actually could be considered a cultural reference as opposed to an English language rule, right? And easy that was makes absolutely no sense it's grammatically incorrect, but potentially it could be someone says that, right? So just looking at the syntax of the English language becomes a very complicated problem to solve, because you have all these different words that come together in different ways. The order of the words matter greatly. It changes the intent behind the statement or the question, and it really adjusts and modifies the expected response or behavior. All right, now when we look at pragmatics, pragmatics means that you understand the situation, the conversation, or the social setting, right? When you have people from different countries, from different cultures, from different backgrounds, it could be very challenging sometimes for even us as humans to understand what is being said, right? I don't know how many times where I've been conversing with someone from another country and they use a cultural reference and then I have to get them to explain it and I don't understand. And likewise, I've had students from other countries where I try to avoid cultural references where I can, because unless you understand the context of how something is being spoken, that can be very challenging. When you ask someone, can you crack the window? You're not asking them to break it, right? You're asking them, can you open it a little bit, just a crack to let some air flow in, right? Similar with a door. Can you crack the door, right? Again, you're not asking someone to smash it in half with an axe. You're asking someone just to open it a little bit. But that's something, when you look at the definition of crack, the definition of crack is a line on the surface of something which has split without breaking, right? So in other words, you'd have a crack in a door or a crack in the window, right? So if I was to change that and just say, is the window cracked? That could mean now, is the window broken? Is there a crack in the glass of the window? And you ask someone, did you crack your finger or did you crack your knuckle? Again, this is referring to the sound that comes from when you pop your joints, right? And you kind of maybe just crack your knuckles, right? Again, programmatically trying to teach a system that when you use crack like this, you're actually talking about a sound as opposed to an actual thing, right? When I say, did you crack your finger? I'm not meaning, did you break it, right? Are you in the hospital? I'm referring to a sound that may have occurred, right? Now, in this case, we're using crack where something is broken, right? So did you hear a twig or a stick crack, right? Again, I'm using the word twig there because that may be a little lesser known, but did you hear something physically make that cracking sound that is now broken, right? You could use a little bit of slang and say, well, did you crack 'em one? And when you say it like that, it means, did you hit the person, right? Did you punch them in the head because of whatever happened or whatever transpired, right? Again, you're not actually, hopefully when you crack someone, you're not actually fracturing their skull. It's, again, a little bit of slang. So pragmatics and syntax are kind of related in that it confuses meaning for not only people, but also machines, because you could have things in different orders, and now you also have words meaning completely different things, depending on the context in which they're said. Now, if that wasn't complicated enough, now we also have semantics, right? And this is where we talk about meaning and context, and it kind of is related to pragmatics. And normally I would do them in the other order, but I just happen to come up with a whole bunch more examples here, and it's a little bit more sort of showing you for an application maybe in a restaurant or a kitchen setting. If your application is in that space, how confusing this potentially could become. All right. So when we say Jaga cooked the dishes, right? what we're meaning is that Jaga's the individual who prepared the meal, right? So when we say cooked, some of the synonyms for cooked are prepare, make, put together, right? I think everybody knows what it says, what it means when we say we're cooking. But when I say John prepared the dishes, what's the difference? Right? If one person cooked the dishes and someone else prepared the dishes, those two words could be used interchangeably. Right? You could use prepared instead of cooked or cooked instead of prepared. They could mean the same thing, because synonyms for prepared include construct, make, ready, or produce. Right? So these may not be, and I'm hoping that when you're building systems for a company, it's not so much that that company is going to use both of those terms, right? Because if I hire someone, say your job is to cook, your job is to prepare, without providing more input, that would confuse people, right? So maybe I meant that you're going to run the grill, Jaga, you're going to cook all the meals, John, you're going to prepare the plates. So in other words, you're going to take the cooked food, put it on the plate, and organize it in such a way that it looks aesthetically pleasing for our customers. And then Jabir is the one that served the dishes, right? So again, serves on the synonyms is obey, present, give out, or set out. So again, if you're talking about a natural language processing system, trying to tease out key words, the context of served could be to obey. And this is where we get completely off the wall responses that don't match with what we expect as humans to happen, right? So Jabir is obeying the dishes, right? That's potentially what a system could interpret this as, right? And then Jake ate the dishes. Okay, I think we're referring to the food that was on the plates, right? And that's the other thing too, is we haven't defined what a dish is. We as humans are kind of assuming that because of what I said earlier, and I planted that seed, I said, okay, this is in a restaurant setting. Without that semantic understanding of this conversation, you could be interpreting this as any number of different things, right? But because I said restaurant, this sentence now makes sense, right? Jake ate the dishes. We're not actually consuming, devouring, or ingesting the plates and the cutlery in this scenario, right? And then Jenny cleared the dishes. So emptied, stripped, removed, take away. Again, all those synonyms that match. So again, what the neural network systems are having to do is do this for each of these words to try to build contextual understanding and semantic understanding of what is being asked, right? Or what's being requested or stated, right? So now, what's the difference between cleared the dishes and clean the dishes? And again, restaurants may use these somewhat interchangeably, or maybe there is no cleared step, right? The part that, because I'm using all these different examples, it's kind of, you can kind of think in your mind, well, I understand the difference between this and I understand the difference between that. But if I just gave you one sentence, right, and I said, your job is to clean the dishes, does that mean that, again, in a home setting, that could mean you take the dishes off the table and you wash them in the sink? In a restaurant setting, that could mean that you have a stack of dishes beside you, which the waiters or waitress brought to you who cleared the table. So without, again, that semantic understanding of where this statement is happening, that changes the meaning of those same words, right? And then Jane washed the dishes. So now, cleaned versus washed. Again, they could be two discrete steps, but again, your understanding of this has probably now changed because I added another option, right? And so another statement where Jack is potentially cleaning the dishes. So does cleaning the dishes mean wash the dishes? Or does it mean scrape the food off the dishes and get it ready for someone to load into a dishwasher or wash by hand, right? And then Jackie returned the dishes. So what does that mean? Does that mean put them back away into a cupboard, ready to be used again? Or does it mean that the customer really did not like their food and sent it back to be redone? Right? So you can see here the semantic understanding is challenging because all of these sentences, if we just put them up and I only gave you that on a flashcard, it would be very difficult, right? And then yes, we also have Skip the Dishes, which is a useful app during a pandemic when you don't want to cook and you can just have stuff delivered to you. And so LUIS is a framework that Microsoft offers. So everything I just described earlier, you can do it locally. You can build an AI system and install it, a conversational AI system that uses natural language processing. There's ways you can do it through TensorFlow. There's ways you can do it through any number of different solutions and these neural networks. But one of the struggles is always getting enough sample data, right? So because so many of these conversational AI systems depend on supporting individuals with different dialects, potentially different languages, you need a much larger sample size. Right? You need a massive amount of samples of utterances to understand both to basically sort out the semantics, the pragmatics, and the syntax. Right? So this is Microsoft LUIS. And so this is sort of showing a little bit around how natural language understanding platforms work. And so I like that the way they've broken this down. All right. So if someone says, and let me just zoom in a little bit so everybody can see. Right. So if someone says, book me a flight to Cairo, this is what LUIS will return. And this is actually in JSON format, and we'll talk about that in a little later. But essentially, what we're doing is grouping together a bunch of variables, right? So the query is word for word what the person said, right? So book me a flight to Cairo. Okay. What the LUIS system did is upon receiving that query and translating that query, so this utterance could have been a text message. It could have been a system where someone was talking over the phone or through a microphone into like an Amazon Alexa or a Google Assistant. And so we won't talk today about how that translation occurred from speech to text, but essentially we somehow got that book me a flight to Cairo. Then the prediction that comes out of this is where the natural understanding comes in, that LUIS is saying that the system feels that the user's intent is to book a flight. And in this case, the intent, so this is the top intent. This is the number one thing LUIS thinks. And then this is the confidence score of book a flight. And so we have top intent, and then we have a list of all the other things that LUIS potentially thinks that this person may want to do. Okay, and you might have seen this confidence index on the Watson video from earlier, right? So that confidence index is a representation of statistically how confident the system is that it thinks it got the right information. Okay, and so here we have, okay, the top intent is book a flight, and it's 98.887482% sure that this person wants to book a flight. Basically, because it's saying book me a flight to Cairo, Lewis is returning that's 98.8% sure that that's what the person wants. It's 4% sure. And again, you notice these don't add up to 100 exactly, right? There's a 4% chance that the person wants to do nothing, because that's always a possibility, right? Maybe it just is it's just talking, right? Maybe it doesn't actually want you to do anything. Maybe people just talk sometimes and don't always expect a response, right? So Lewis thinks in this case there's a 4% chance of that. The other thing that's showing up in the confidence, in the intents, is location finder. And because Cairo was mentioned and Lewis recognizes that Cairo is a place, it's thinking there's a 1% chance that the person who said, book me a flight to Cairo, just wants information about Cairo, wants to know something about Cairo. Where is Cairo? That sort of stuff. The reason why this is only 1% has to do with the model that's been trained in this particular situation. So because in all of the training data that was applied to this model, the keywords flight and book greatly elevated this. Now, the other part I missed on this, okay, so this particular example was actually a travel website. So that's going to influence the data that comes in. So these are all intents that may have been predetermined or pre-configured by the application. There's a 0.03% chance that this is a reminder. And that's times 10 to the negative 7. So there's a very, very small chance it's a food order, right? So these are all intents that the model has been trained against as possible outcomes. Okay, so Lewis is, because again, the contextual use of the language will change. If this was not an application for Expedia, if this was instead a bookstore, that would change the intents and the confidence indexes, because the word book could mean that you're looking for a book about Cairo, right? As it's reading through there. So this has to do with these scores come up and are determined as a result of the data that's been fed to the model. Okay. Now the last part is this concept of entities. And so when you're talking about booking a flight to Cairo, you're talking about book a flight is your intent, and Cairo is the location that you'd like to book the flight to. So part of the system would be to accept, to understand the intent is number one, but then also to determine, is there any entities? And entities, the easiest thing to think of them as variables, right? So if I said, book me a flight to New York, right? The entity would be New York, right? Because I'm looking for my location to be New York. The whole key here of what this system is doing is translating what the person says into a format that a computer can now understand. So now you could build on top of this an application that says, you know what, if the confidence score is 70% or better, and I'm just making that number up, you could pick whatever number you want in your application. But if the confidence score is 90% or 80% or better, or 70%, whatever it is, and I have a location, I'm now going to look for that information. And the benefit to this is this all happens in near real time. So by the time the person has uttered the sentence, within a second, you could already be returning results for flights to Cairo. Now, what's missing here is, where is the person located? right? We're assuming that the system potentially already knows where they are, because when you're booking a flight, as you know, you have to have a where are you coming from and where are you going to. So that's not in the utterance. So now we would look at and infer from another system, do we know the person's current GPS location? Do we currently know their home address? What other information do we have on their profile that we can put together with this system and what has been asked for to try to come up with a response? And to do all this effectively, this is where we need neural networks, because we can't just predetermine all of this stuff, right? We can't predetermine all the different locations where someone's going to be. We can't always say, you know what, we are always going to assume the person is in New York and wants to go to Cairo, wants to go to Tokyo, wants to go to London. It depends. Okay. So in this case here, we're saying order me 2 pizzas. So now, based again on this training data in this application with these intents that have been identified, now we're 99.9% sure we want to order pizza. There's basically a 6% chance we don't want anything. We're not doing a location, we're not doing a reminder, we're not booking a flight. And now we have a couple of entities here. So the entities would be or included as part of the definition for the intents. So the food order intent might accept multiple entities, right? So for example, it accepts the quantity or number and the food type, pizza, right? Now, obviously we could provide additional information. We could specify what do we want on our pizza? What size is the pizza? All of these would now be different entities that are associated with that particular intent. So if the person does not include them, then we would prompt them and say, okay, based on your last order, you ordered 2 medium pizzas. Is 2 medium just cheese pepper or just cheese pizzas? Is that what you'd like? And you might say, no, I'd like vegetarian this time. And so now it's okay, I'll order you 2 medium vegetarian pizzas. Is that correct? Right? So what we're doing is, when you think about traditional programming, normally you would do things like on a web form. You would fill out, okay, I want 2 pizzas and I want them to be medium, and you'll choose the size and you'll choose your toppings, and you'll choose whether it's for delivery or pickup. When you're talking to someone, this is part of how the conversation evolves. So it ends up being very dynamic, right? It has to be part of the dialogue, right? And just to show here, this is now an example that you see in a lot of mobile applications. Where's the nearest club? So in this case, the location finder, it's pretty sure it has an 89% confidence that that's what it is. The next closest one is 0.03, other than do nothing. So it thinks that it's a location, but there's no entities. So now this is where you would have to program into this intent the ability to figure out where are you currently. Because it's nearest, that's always reference to where you are. So again, if you're talking about this in Siri or in an Android phone, it's always based on, well, I know where you are because you have location services turned on. If you do not have location services turned on, I will ask you to turn on location services. Or I will ask you, where are you? Right? What city are you in? Those types of things. Okay. So I'm doing this in a little bit more detail just to help you understand kind of how these systems dissect the query and sort of what the responses look like.